10. So now we're going to take a single bigger problem of moving a particle in a certain direction, finding out where it hits something, reflecting it, and finding out where it is after a certain amount of time. And we're going to find a way to apply all of those methods, all of those vector mathematics that we've been looking at before, to solve this single problem. So to begin with, let's just draw a nice, well, a crude image of what we have here. So I'm going to look at the numbers here in the rectangle. Highest number on the x-axis is 9 and 8 on the y-axis. So let's set up a little coordinate system here. I think it's all in the positive quarter of this coordinate system. So if we take it about here, like so, 9 there, 1, 2, 3, 4, 5, 6, 7, 8, 9, and just about the same size of this here, 1, 2, 3, 4, 5, 6, 7, well, 8 up there. Okay, so the rectangle that we're looking at, 3, 1, and 1, 4, 1, 2, 3, 1 there, 1, 4 here, 9, 5 here, and finally what, 7, 8, 7, 8 up here. Okay, it's not a great image, but sort of gets the general gist of it. Okay, so we have a particle positioned at 1, 1. Call this point A. We can call this here P1, P2, P3, and P4 up here. And that particle is moving along the vector 1, 5. Should go like 1, 2, 3, 4, 5. So if we draw that starting at the particle, let's just mark the particle specifically and draw the vector here. That's more or less the vector. And we'll call that vector C. Vector C equals 1, 5. Okay, and the point A here equals 1, 1. So the idea here is to find this point here, its exact location, figure out when that happens, so how much of the time is left, and then continue along the new reflected vector for the amount of time that's left. And it states here, it asks at which position will the particle be at the time 1.0. So if it were uninterrupted, it would end up here at the time 1, since it's traveling along c for 1 full length of c per second. But what we're going to find out is where the intersection point is, and once we've figured that out, we're going to reflect it off of the correct side. So in the image we can see that it's the side between P1 and P2 that we're going to be looking at. But in a program we can't really see that, so we really need to go through calculations that'll make sure which side it is actually that we hit, which of these sides can we hit, which one is it that we hit, and at which time. So we'll go through a few methods that can help us with this. Since we see it on the image, let's just start with finding the actual point where it hits on the line between P1 and P2, and then we'll look at which methods we can use to eliminate the other sides. Okay, so yeah. Okay, so to begin with, we have this line here between P1 and P2, and we need to find a way to make that some kind of point normal form. So P1 equals 3, 1, 3, 1, P2 is 1, 4. So a vector between them, this vector here, let's just call that V. Say the vector V equals P2 minus P1. So that'll be 1 minus 3, which is the vector minus 2, and 4 minus 1, 3. So this is the vector V. Whoops. What we're interested in now is, so this is a vector that's parallel to the line that we're going to be looking at, but we want a vector that's perpendicular. So we're going to just say n equals V perp, which equals, if it's going that direction, alright, this vector would then be minus 3 minus 2. We could just as well decide that n is minus V perp if we'd rather use a vector with non-negative numbers. It doesn't matter which normal vector we use. So just for the ease of looking at this, let's do this like so. Okay, and say n equals minus V perp. Actually, we could just erase this as well. Like so. And equals minus V perp. Anyway, so we have a normal vector 3, 2 here, and we can draw that vector on the image as well. It'd be, if we're going to use for the point normal form the point P1, which is fine, we'll use this point here, and we'll use a vector that's 3, 2, which would look like this. So that's our vector n right there. So we're going to use the point P1, we're going to use the vector n, and for the ray, we're going to use the point A, and we're going to use the vector C. So we can also say P1 now equals B. Same point, different name, just to use the formula that we have, which tells us T hit equals n dot B minus A. So we're using P1 as B, we're using the position of the particle as A, divided by n dot C, where C is the direction vector of the particle. Okay, so now we simply have to figure these things out. We can go up here and say B minus A, just to take that specifically. So P1, which is B, was 3, 1. So we can also say P1 is now B rather than P1. So B minus A equals 3.1 minus 1.1, which is 2, 0. So that's the vector between those points. So here we have n 3, 2 dot 2, 0 divided by 3, 2 dot, and our vector C was up here, 1, 5. Okay, so 3 times 2, 6 plus 2 times 0, so that's simply 6. Here we have 3 times 1, which is 3, plus 2 times 5. That's 10 plus 3, that's 13. Okay, so 6 by 13. Let's just leave it at that. Okay, so now we found the time of hit here. So it happens at 6 by 13. So rather than actually calculate this for all the other lines, we can now do exactly the same thing for the line between P2 and P4, P1 and P3, P3 and P4. And we can do this for all of them. And then we can look at this T hit here. We don't have to calculate P hit yet. Just look at the T hit of all of them. If we want to do this in a program, we do it for all 4 lines. We check the T hit and we take the T hit that's lowest but still positive. A negative T hit, for instance, if we look at our picture, when we take the line we've already taken here, we're going to get a positive T hit. When we take this line, we're also going to get a positive T hit. And judging from the picture, it's also going to be somewhere between 0 and 1, so it's within our range. However, the one we've already found is smaller, so that's the one we're interested in. When we take this line here, we're going to find a hit point that's somewhere up there. And it'll have a positive T hit, but it'll be way bigger than the other two, so that's not what we're interested in. When we take this line here, however, we're going to find a T hit that happens somewhere down here. It'll be a negative T hit, so that's something we're not interested in either. Also, when we do this in a program, once we've actually found a T hit that we're interested in, we now also have to check if that T hit actually happens between the points P1 and P2. So if it happens between the points P1 and P2, then we take the smallest of those and choose that. So we do the T hits. Anytime we find a T hit that's within the range that we're looking at, we'll calculate the P hit, see if it's actually between 2 points, and continue from then on. So now we know this is going to be the lowest T hit. We're going to calculate P hit now, and we're going to set up a little check to see if it's actually between the 2 lines. So we have T hit there. Next is P hit. So P hit is just the formula for the array, the parametric form of array, A plus T hit times C, using the value of T hit. So in our case, this gives us A was 1.1, T hit was 6 by 13, times C, which was 1, 5. 1, 5, 1, 1. Okay. So let's see what we get here. That gives us 1 and 6/13. And then it gives us 1 plus 5 times 6/13. That's 30/13, which is 2. So we have 1, get 3, and 4/13. Okay, so 1 and 6/13, 3 and 4/13. So that's the hit point that we have. So now we check. Now we check if P hit is between the line segment ends. And all we need to do is just check if either the y or the x values are in between. So let's just look at the x values now. So the x value for P1 is 3. The x value for P2 is 1. So we just need to see is 1 being P2x smaller than P hit x, which is 1 and 6/13, which is smaller than P1x, which was 3. Okay, so this is true. Which gives us basically a positive check here. So that's nice. Now we know that the point is actually between or inside the line segment. So all of this is good. And now we know that we're actually hitting in the spot. What we need to do now, we've actually found the point as well, so we know where it hits. Now we just need a new direction for A. Since the old direction for A hit here, we need to say, okay, now we're going to take this normal here n and imagine that it's here. It doesn't really matter in which direction this n turns. We could imagine if we have the other way around, it's here. And then we take A and we're going to say we need to find the reflected direction, where this angle and this angle are the same, and this will be our new vector. We'll call it R here, but that's the new vector for A. It'll be our new C. So now I have to find that vector, and once we found it, we're going to take the amount that's left of t from the time we started until the time we want to end. In our case, that's the time 1. In many cases, it'll be the total frame time. We'll subtract from that the t hit, which we've already traveled, and so say what's left of it is then what we have yet to travel. All right. So we have a formula for this. So right now we found the point where we hit, and it doesn't really matter where that is for the reflected direction. The only thing that matters is the normal that we have, normal n. So our normal n is 3,2. However, we are going to have to normalize that or divide by its length. So the formula that we have here for the reflected direction looks like this. R equals A, which in our case is C, minus 2 times A dot N times N, which is the vector, if N is normalized. However, we can say this divided by N dot N. We'll add the normalization into the formula as we go. Since we have a non-normalized n now, we'd have to add that. So this is the length of n squared. And since we have 2 instances of n here, then we can divide by the length squared to normalize both of those as we go. So in our case, this would be R equals, so A is C, the vector A equals C, which equals 1, 5, N equals 3, 2, and that's all we need. So we have 1, 5, minus 2 times 1,5 dot 3,2 divided by 3,2 dot 3,2 times the vector 3,2. This gives us 1,5 minus 2 times, 1 times 3 plus 5 times 2, that's 13. We already had that dot product earlier. So then we have 9 plus 4, which happily also gives us 13, interestingly enough, times the vector 3,2. So this equals 1,5 minus, so we have 2 times 13 by 13 is just 1, so minus 6, 4, if we just multiply 2 into this set here. Alright, that gives us the vector minus 5, 1. So let's look at how that looks on our image. Minus 5, 1. We have 1, 5. And minus 5, 1. Yeah, that's more or less. Minus 5 in this direction, we don't have room for that. But if we go like back about 2.5 and then up 1/2, it seems like it could be the right direction. So let's use that. It's correct enough. Let's see, back to the old drawing board. Okay, so that's the vector we're going to use. So we're going to say minus 5, 1 is the new direction. So the particle that we have the point A. It needs to take its whole direction, which is here, the vector c. But it needs to do that, it needs to travel this vector here, which is c times t hit. Then it needs to change directions and say the new vector is now this vector here. That was too thick. This vector here, which is now the new vector c. We can just call it c new. But it has to travel that vector. So c new times 1 minus t hit, which is the rest. Or, as I said before, in the case of using the frame time, it will not be 1 minus t hit, but frame time minus t hit, or delta time minus t hit. So we know that after traveling c times t hit, it'll be at the hit point. We've already calculated that. It's here. 1 16/13, 3 4/13. We have 1 6/13, 3 4/13. So now we have to travel from there. So that's our new A. This is kind of our new A, or our temporary A. So A moves to here first, and then we add the other vector. And in the program, once we've moved A to here, then we actually change the value of A to that, and change the value of A's traveling vector to the new vector. And the old traveling vector doesn't matter anymore because it's already reflected. Okay. There. So finally, we now have 1 6/13, 3 4/13. That's our new A. So final A, call it A S for solution, equals this intermediate A plus 1 minus T hit. And 1 minus T hit is 1 minus, where's T hit again here? 6/13. So what's left of that is 7/13 plus plus 7/13. We can just mark that here with 1 minus T hit. 7/13 times the new vector, which is minus 5, 1. Minus 5, 1. So this gives us the final answer of 7 times 5 is 35. Not plus, but equals. So we have 35 by 13, which is 13 would give us 39, so it's 2, it's minus 2, it's 26, so there's 9 off of that, minus 2 and 9/13, and 7 by 13. So this is our final answer. This is the position of the particle after it's traveled for 1 second, and inside that 1 second reflected off of this line here. So it said it was, no, this is not correct, sorry, we forgot to actually add the point itself. I'm gonna erase this. What we need to have here is, okay, so this equals 1 6/13, 3 4/13, plus what we had earlier, which was minus 2 and 9/13, and 7/13. So this is what's being added. This is where we were at. This gives us, however, okay, 9/13 subtracted from 6/13. That's okay. That's, so we have 10/13 left. Minus 2. So that's minus 1 and 3/13. And then we have 3 4/13 plus 7/13. 4 plus 7 is 11. So that would be 3 and 11/13. Okay, so this is our final position, and now we can look at it on the image and see if that makes sense. So minus 1 is 3/13. It's just beyond the picture here. And then 1, 2, 3, and 1, 2, 3 and 11/13. I guess it's not far off. It ends up somewhere around here. If we did any wrong calculations, it doesn't matter because we did the method correctly. If we dropped a minus somewhere or a single 13th, that's okay. So one more thing that's nice to look at here. So this is the answer to the question, that's fine. But one more way that we could have to eliminate some of these sides is that if we make sure that when we make the normal vector for each side, the normal vector is pointing out from the box. Not into the box, but out from the box. In that case, we can actually say we can take a vector from any point on the line. So take a vector from P1 to A and the normal vector, and we can check the angle between them. If that angle is acute, and we don't even need to check the entire angle, we just need to take the dot product, and if the dot product is bigger than 1, that means we have an acute angle, and that means that the point is at the front side, so it's outside the box. And that means that we could actually hit. If we look at all of the other ones here, you can see that this normal here and the vector to A would give us an obtuse angle, an angle that's bigger than 90 degrees. That simply means that we get a dot product of less than 0, a negative dot product. A negative dot product between these vectors tells us that A is actually on the other side of this, on the back side of this side, meaning that if it were to hit this side, it would be hitting from the inside. And if we have an enclosed box, we can say we're never going to be interested in hits from the inside. So if we begin by taking each of these lines in this way, we can look at it a bit clearer here with this line where we haven't drawn so much. So we take this line here, we take its normal here, n, and we take a vector all the way to where we're checking, A here. We take the dot product of these two vectors, it gives us minus, so we can see, okay, if this were to hit from any direction, it doesn't matter where it's traveling, the hit would always happen on the back side of this polygon, and we're not interested in that. This one as well. So in this particular case, if we would start with that check, we could eliminate this side, and this side, only having to check this side. The way we do it now, instead we check all the sides, we find t hits. We're going to find this side anyway because it has the lowest t hit, but we could eliminate it beforehand in the other way. Just bear that in mind. So here's our final answer.